Welcome to today's lecture on data inputting and editing in GIS. So, I am Shiva Reddy, and I will introduce you to data inputting and editing in GIS. Right. So, before move further, what we will understand first is how data used to be collected earlier, how we are doing in GIS, and then we'll see various sources and error which are kept in GIS. Right. So if you see this picture, uh, earlier when data used to be collected from the field using surveying instruments, like if you can see here, the surveyor is using plane table and using telescope and theodolite measuring angle and targeting feature and corresponding record he will make on the paper, and later he bring that into a desk in office and make a fair copy and carefully printed one, and these are called topo sheets or maps is created. That's how thing used to be earlier. But if you see now, it is much smarter, much easier, and more instruments are being used. So now you can collect data from the aerial aircraft. So again, uh, if you see some years back, the aircraft used to have, like 20 years or 25 years back, used to have an analog camera or the cameras with negative. Now everything is equipped with digital camera. Similarly, you can carry your personal digital assistants, tablets, mobile devices along with you in the field, and you can directly draw GIS features. And in the last one, which you can see in the bottom, is called heads-up digitization, where basically you use the digital images, bring it to a GIS software in computer, and there you interpret and create it. So, so overall, these two slides summarize how things used to be done earlier and now how it is being done, right? So we'll see what are because in GIS data is the core and most important thing. So we'll see how data used to be collected earlier, right? So and what how we can bring that into GIS. So what are various sources from where we can get the data, and how that from that source directly how we can use into GIS. So data source and corresponding input. So if you say data source can be one way can be manually digitizing from image or map sources. So what can be image or what can be map? So it can be a manually drawn map from topo sheets, because if you want a record of 1970s or 1700, 1800 or 19th century, 16th centuries. So for that, I cannot collect data using the equipment which I have now. So I have to rely on the already drawn maps, already available records, or mostly they are manually drawn and they are not in digital format. So that they can work as a source. Similarly, you can have a list of coordinates and also associated tabular data may be available in digital format or non-digital format. So basically for each location, you have a coordinate and also associated tabular data, non-spatial data is available. Then again, I'm talking about aerial photographs here. So when I say during this course of lecture, photograph means they are different from images. While image is a digital one, photograph is the positive developed from the negative, right? So earlier, before digital camera, we used to have a cameras which create photographs. So we can have an aerial photograph from where also we can extract features. Mostly in GIS, we take vector data, consider vector data. So we digitize point, line, and polygon, right? Another source can be field coordinate management that I have shown you the picture. So these are the coordinates which are measured from the field, and they are done using coordinate surveying or GPS based surveying. And the last one is the source is the image data. Image data means this data is already in digital format. So again, these data can be classified and then converted into vector, or it can be manually digitized, or there may be a slight cases or very rarely you will be directly creating raster data. So these are the various sources and input methods which are used in GIS. Right? So let's see one by one. right? So this is called manually drawn maps or the topo sheets. So this is the primary source. If you go back to any uh, few centuries, you want to know what features were there in that time, you need to rely on the topo sheets. So digitizing from the topo sheets require that first we understand the topo sheets, then based on legends, we can understand what are different features, and then we can digitize point, line, and polygon. And what this digitize means, that also we'll understand in a coming lecture. So topo sheets are prepared based on the coordinate surveying. They are carefully printed and plotted and printed in a paper or cloth. And these topo sheets can work as a source. But as you know that this paper-based map or the cloth printed maps cannot be directly ingested into your computer. Computer cannot directly read it. For that, you will require a special instrument called scanner. That also will see what are different kind of scanner, how scanner does that. Another source, as we discussed, is a field measurement, where coordinates are captured right from the field. So if you see here, this instrument is called total station. Why total station? Because this is not a single station or single equipment. This equipment is consists of theodolite. Theodolite is a device which measure angles, both horizontal and vertical angles. Then we have a telescope, which helps you targeting the feature so that correct angle can be measured. Then, so if you can measure angle, target a feature and measure angle, that is not sufficient. You want to know the distance also. So that's why there are instruments which can measure the distance. So electronic distance measurement, EDM, or distance measuring device is also integrated in the device. So what basically does is it throw a light laser beam, it hit the target, it come back, and based on the time of flight, we can calculate what is the distance of the target from the location. So in this way, we can. So if we combine this electronic distance measurement devices plus theodolite and telescope together, it becomes total station. So if you know the distance, if you know the angle, then you can calculate relative coordinate of the target with respect to the current location. Only thing is current location should be known. So what we can do first, current location, relative location of the target you can know. Then once the current location is known, that again from the already known location, you can know the current location using same technique. So coordinate surveying is used. So it will work on that principle. While GPS based survey, you cannot know the location of remote object directly. In GPS based survey, whatever is the target, there you put this GPS antenna. So if you see on the top, this is the GPS antenna, right? And so based on the satellite constellation, you will it will measure the coordinate. I think Monday you will have a lecture on introduction to GNSS and GPS, where we'll know much more detail about it. But what for the sake of completeness, I will summarize it. How GPS work is, this antenna will receive signal from satellites. So there are satellites, GPS constellation, there are many satellites. So at least 3 or 4 satellites should be visible from your antenna. And the signal received from these satellites, again, it's a passive device. So basically, once signal is received, it goes to the controller. Controller measures the time of signal start time and the reception time. And based on that, you calculate distance of this antenna from the known satellite, right? So if I calculate distance, if I know the distance from the known satellite, if I have more than 3 or 4 known satellites, so intersection of that will allow me or will help me to approximate my current location. So on that principle, GPS works. So basically, GPS constellation satellites are keep sending. The satellite don't receive any data from the antenna or the receivers. The GPS receiver is a passive device. It receives the signal from the all the active satellites in that area, and signal consists of the start time, and while receiving it, record time is maintained, and based on the time difference, the distance is calculated from the known location of the satellite. And each satellite, along with this time, also sends its own location. So you know the exact location of the satellite, and you know what is your distance. So if you have such 3 or 4 anchor points, so you can traverse back to your what would be your current location. In that principle, GPS work. And these signals are recorded in the controller, which is here. So the height of this antenna is subtracted from the whatever coordinate you observe to get actual the ground coordinate. Right. And if you have image data, modern day satellite or aerial aircrafts, they give us an image, means digital data. They can be directly ingested into GIS and interpreted to make different GIS maps. Right. So now coming back, if you don't have a digital image, you have a manually drawn map or topo sheets, how to go with it. So you have to use scanner. So we have, if you can see, there are two type of scanners here. This one is called drum type scanner and this is called flatbed scanner. So in the drum type scanner, you roll up your image and this map, and the map is scanned. So advantage of drum type scanner is that only width is a limitation and length is not limitation, because everything is rolled up. So you can have as much size, lengthier maps can be easily scanned. While flatbed scanner, it requires a lot of space to scan a bigger image. So what scanner does, it converts this paper-based map into a digital image, right? And then another concept is called digitizer. So if you see, modern day digitizer means you scan a, convert it to a digital image, bring it to a GIS software, and then in your monitor you can do digitization. But before that, intermediate, if you see maybe 25 years or 30 years back, this was the process. In this process, you use this paper-based map, put on a digitizing table, and there they have a grids, and based on grids, now you put your cursor here and record every point, and this is recorded in digitally, and this is called heads down digitization. This used to be there. Currently, it is what you say. This is not so much relevant because everybody is using scanner and using digitizer, which is heads up approach. So as we can see, scanner can be of two type, drum scanner and flatbed design. So, and the we measure the quality of telephone mobile screen, quality of LED screen in dot per inch. Similarly, scanners quality is also assessed using dot per inch, right? So basically it tells how many dots would be there in per inch of the scanner, or per inch of the paper, how many dots will be captured. So to understand that, let's go with an example. Suppose a scanner is there, right? It has 1,000 by 1,000 pixel and paper size is 10 centimeter by 10 centimeter. So what it means, in the 10 centimeter width, you have 1,000 pixels, right? So if I want to know how many, or each pixel, let's talk as a dot. So if 1,000 dots are there in 10 centimeter, so how many dots would be there in 1 inch, right? So if you look into this, we know that 1 inch is 2.54 centimeter. So the 2.54 centimeter is the length of the inch. And in 1 centimeter, we have 100 pixels. So once I multiply 2.54 into 100, so 254. So this becomes the answer. So your DPI will be 254, right? So dot per inch is the quality. If you have more dot per inch, you have a better quality scanner. And so what generally people do is, based on the accuracy or mapping unit, minimum mapping unit of the map, you decide DPI. So minimum mapping unit of the map is the minimum measurement which is possible to be taken from a map. So that depend on the input instrument which is used while creating that map. So if suppose topo sheet is created using a pen or paper, pencil, so tip of the pencil will become a minimum mapping unit. So that will be around 0.25 millimeter. So we have to make sure that our DPI is such that it will capture at least the minimum mapping unit. So now if you see the process, which is very important, like manual digitization process, basically this is the process mostly used. And what we do in manual digitization process is we scan a map, basically paper-based map, and or we directly take image. If image is there, you don't need to scan. If image is not there, you scan and convert that into an image, and that image will be bring into GIS. So again, image has two possibilities. Image may be georeferenced image directly getting from a satellite agency which directly give you the georeference image, or image may not be georeferenced. If image is not georeferenced, then we have to collect ground coordinate points. So what we mean by control points of the ground, we have to collect ground coordinates of the control points. What we mean by control point? Generally, control points are those points which are available in the image and also whose ground coordinate is known or which can be found out in the ground. So control points are those common points which can be easily identifiable at the image. At the same time, we can go to ground and calculate its ground coordinate. So first see the image and find out those control points for which you want to collect the ground coordinate. So in the image, there may be junction of road, there may be river junction, there may be some prominent thing which are easier for us to go through ground and identify them. So next task is to identify control points in the image and also find out the ground coordinate. How to calculate or collect ground coordinate? You may one simple way is to identify in the image identify an object or a place mark and go to the ground with a GPS or some instrument. You measure the coordinate. Second option is you go to another georeferenced image, high resolution georeferenced image, and try to find out its coordinate from the high resolution georeferenced image, the same object which is available in the image in the question. Right? So once you know the ground coordinate, next is to digitize this. Basically, digitizing means you in the image you mark all the control points. Along with that, you enter its ground coordinate. When you digitize your control point, automatically image coordinate is captured. So image is an arbitrary coordinate system. So some coordinate will be captured and you enter its ground coordinate. Now, because you have set up 4 or 5 or say 6 control points, so set up 6 points for which you know both image coordinate and the ground coordinate. And our aim is to convert this image coordinate into ground coordinate, right? So for that, what we'll do is after digitizing control points, we calculate what is the transformation parameter, what is the relation between the image coordinate and ground coordinate. Once we get this transformation parameter, calculate that, we will apply it to entire image. This is called transformation or registration. And once you apply that to entire image, you will get an image which will have a coordinate system same as the ground coordinate. Now, because now your image is georeferenced, if you digitize anything, they will also have the coordinate with respect to ground, not with respect to image. So this is in short, the georeferencing process. If you see further, after georeferencing, you want to digitize. So digitization can be done in a stream mode or in a point mode. So what we mean by stream and what we mean by point is, right? So when I do streaming, stream mode means I don't click, I just move. And as I move, digitization happens. And in the point mode, basically, I am clicking, I am creating vertices, and these vertices are joined to create a line and subsequently polygon. So stream mode is very helpful for people who are very artistic and who have good control in their hand. And point mode can be used by any person because you just keep creating points, and these points subsequent points will be joined to make a line. So scanning, again, if you see in the scanning, if you see here, what we know the digitization process, we have seen the scanning here. So what will happen when you do some scanning? So say there are two linear features, linear junction is there, this white pixels. But once you scan, sometimes you may tend to find this kind of zigzag boundaries. And I think most of you might have guessed these zigzag boundaries are due to abrupt pixel boundaries. Pixel boundaries are suppose pixel in rectangular shape. So they will not smoothly change, they have abrupt change. So this boundary here, left side is black and right side is white. So this kind of boundaries will come and that may not look like a real feature, right? So this can So while scanning, you get this kind of images which are pixelated. That's why automated digitization is often not practically used. Manual digitization is done. So suppose you want to do automatic digitization, then some further steps are required. So like here, if you see, let's see an example. Here, a hypothetical image, we have different colors. And based on the color, say I want to convert into a polygon. So yellow will become one polygon, green will become one, red will become one, and purple will become one polygon. So this is exactly, if you trace out the boundaries of yellow one manually, this is exactly called digitization. And but if you do it automatically based on pixel value, that again, this is a very hypothetical and simple image. So automatic digitization possible, you convert from raster to vector, and this will become uh, vector data, and basically that means you have done automatic digitization. But in real world scenario, automatic digitization are not possible, right? So because there may be for automatic digitization, the maps need to be very clean, and you need to easily identify line, polygon, everything. But let's go back and understand what we do in digitization. Still now I'm talking about digitization, but not explain much in digitization. So in manual digitization, we have two concepts. One is called vertices and other called node. So node basically determines the start and end of any linear feature or any vector data. So node 1, node 2, this between that, when you join, you get a linear feature. So nodes decide the start and end, while vertices, you see here, node from this node to this node, right? From this node to this node, we have two features. So while feature number 1, which is a straight line, right? And this is don't have any vertices, start node here, end node here, so on. But another feature, we have two vertices, right? So what happened is, now if you see both the features and just compare nodes, for both linear feature, nodes are same. But while nodes decide the start and end, the vertices decide the shape, because these have more vertices and these vertices have different shape. It gives different shape to this linear feature than the straight line. Right? So shape, so vertices define the shape while nodes define the start and end. So when digitization, automatic digitization, I told you when maps are not neat and clean, and as we saw a hypothetical example where boundaries are not very much clear, so automatic digitization may not be work. But manual digitization means human beings are very good at interpreting images, so interpret and they digitize. So what happened? Digitize means they create a point, line, or polygon. They can do in point mode or stream mode, as I discussed. Let's say we will do in point mode. So basically, we are start creating nodes and vertices, and that will be joined. So because it requires a manual intervention again. So from manual map, you scanned it, bring back into GIS, but again now you're manually digitizing. So again, humans are involved, and so manual, there can be some error which can occur. Some may be due to limitation of our cognitive ability. Some may be due to limitation of our physical what you say, physical limitation of our organs like hands, fingers, movements, and other things. So what happens in manual digitization? Some of the errors we will try to understand, and we'll also see in the lecture how this error can be avoided. Right? First thing is to, if you want to avoid error or correct error, you should know. You can be prepared if you in advance you know what kind of error can come. So one such error is called undershoot. Another error is called overshoot. These are very common and very easy to understand. Undershoot error are those places where while digitization you wanted this node to join this line, but you couldn't. Overshoot is you wanted to join this line, but you crossed it. And if you see in GIS or in modern day digital LCD monitor, it become almost impossible to exactly pinpoint, right? Exactly pinpoint to the edge on this road, because the width of the linear feature is infinitely small. So what happens is, it is nearly impossible to target this feature. So, and either you will be doing undershoot or overshoot, but to avoid this kind of error, we can use a concept called snapping that I will cover in the later slide. But these two errors are very common, undershoot and overshoot, and we'll see how we can avoid it or at least minimize it. Second thing, while digitizing, you maybe have a dangling node like here. So dangling node means, so though this is a closed structure, say polygon, but there is some extra node happening here, and that's why this is called dangling node, and this arc is called dangling arc. So this is also one kind of error. So there are two scenarios. One scenario, there may be really existing nodes which such features may be there. So then we'll not call it dangling node. Dangling nodes are those nodes which are created and which are not linked with any linear features. So basically error. Similarly, these are the spatial error which can happen, but sometimes while digitization, not only spatial data like a shape or figure is important, but also the non-spatial or attribute data is important. So attribute label may not have written. So that can also give an error, right? So missing the polygon label or missing the point label, that can be an error. Similarly, when two lines cross each other. So again, here we are assuming that we are digitizing in XY plane, but there may be, so what happens is in ground, there may be scenario of overbridge or underbridge where XY may be same for 2 points, but they may not be crossing. In order to avoid confusion, what GIS practice is, if there is a line crossing, there should be a node. So a node must exist in all crossing. If node is not there, the GIS or computer will assume that these lines, though they have sharing one common XY, they may be having different Z option or different height. So that's why the crossing will not be recorded. So whenever there is a crossing, we should create a node. Right. So let's see what are the way to avoid this kind of error. So if you see here in this image, already people have digitized. So data inputting, editing. Inputting is one which you have done. You imported, you scanned a map, you georeferenced it. Now you digitize it. So inputting is done. But editing is after inputting, you want to avoid errors. So like here, if I see, right? So if I see this red one, this portion, and this polygon, right? So these two polygons, though they are here, they have some problem. So one is polygon, another is a linear feature, but they have some problem. So we are not sure this polygon belong to whom. And if you see this boundary, is this boundary of a forest or it is a road layer? So again, it has a confusion, right? So how I can correct these errors? In order to correct this error, one thing is simple. The feature like here, this polygon feature, which is not identifiable or relatable to anyone, you simply delete it. But this is the most basic and simplest example. Whatever feature has error, just select it and delete it. But what will happen if you keep doing that? At the end, you will not have any feature to edit. All feature will be deleted, so you have to digitize again. So not always we will be able to delete all the problematic feature. In that scenario, what we do is we do the editing. So you select a feature. So as we understand, though node defines the start and end, the edges, vertices define the shape. So in order to correct the shape, you can move the vertices, all the vertices, and I have moved these vertices and save it. So modifying and editing, modifying an edge is an option where you generally simply move or relocate the vertices to a new location, and by which also error can be corrected, right? So this is one. Second, now I told you earlier also while discussing overshoot and undershoot, and there are many such error which can come, and these kind of error can easily be solved by using the snapping concept. So if you see the snapping, what snapping means is whenever a vertex or node is close to nearest vertex or node, it will join directly, right? So there are different software, commercial or open source software provide you different option, but it may say edge snapping, line snapping, vertex snapping, or so what basically snapping is, it try to find out nearest vertex or node and attach to that. So if a line snapping is on and you are digitizing, so line snapping is on and you are digitizing and you move your cursor anywhere within this zone, automatically a new vertices or node will be created and it will be joined. So if line snapping is on, suppose line snapping is not on, only point snapping is on. So in that case, what will happen is, if I have a start node, end node, so some software provide you node snapping, some software provide you as vertices snapping. So if you bring your any point, if you only say node snapping is on, so it will join to this point, or it will join to this point based on location. Otherwise, it will not join you. So line snapping means your whatever your distance and your cursor within a threshold limit, it will join to the line and will new vertices or node will be created. Point snapping means all existing points. So again, it may be vertices in the current existing line or existing points. If any new point is created with fall within the specified distance, it will be joined together. We can see example here. So suppose I am digitizing and I have put snapping on, and my snapping tolerance is such that say 3 pixel or 4 pixels. So this kind of circle is created. So whenever I'm digitizing, whenever I move my cursor and click, I will try to find out within the 3 or 4 pixel radius based on this, or within this radius, if any points are there or not. If not there, it will not do anything. If it is there, like you see here, it is there. So within that, this line comes. So what will happen is our new node will be attached to this line. So if you don't use snapping, it could have given you the undershoot error, but because you're using snapping, undershoot error is removed. Similarly, suppose you're digitizing and within the threshold limit, already one point exists, right? So what happens is it will be joined to the existing node. So again, undershoot error is avoided. Now, this is a typical example of overshoot. So this has happened here because snapping is not used, but because we have used snapping, so it know within the threshold already one line is there, so a new vertex will be created on the line, and hence this can also be solved. So we have seen that if you use snapping, most of the time undershoot and overshoot error will be automatically reduced, and based on your requirement, you can tweak around the threshold values. So because this vertex or this line is not within the threshold limit, so this is still independently existing. So now we have seen that by using snapping, we can avoid some error like overshoot error, undershoot error, and consequently, if you don't have overshoot, undershoot, so there is less chance that dangly node will be there. So most of the errors are removed. But non-spatial data error can be removed by putting a not null constraint to the GIS data digitizing process. But now let's see, manually digitizing, there can be two kind of, like in our society, like in normal day-to-day life, there can be two kind of people. So one set of people will generate this kind of digitized map, and one set of people can generate this kind of map. So while digitizing vertices and shape, so if you put few vertices, the shape will not be in proper form. So this can be one example where a digitizer is feeling lazy or he don't want to work much. So he created one node here and after here. So though it should look like a curve, it is looking like a what you say, step function, which suddenly jumps values. Then again, it will jump from here to here. So there's no smooth curve here. And when you see here too many vertices, though curve is very smooth, but too many vertices are created. And if too many vertices are generated automatically using a function, no problem. But this is manually done, so there will be a lot of time will also consume. And due to too many vertices, it will increase complexity in the processing and storage of the data. So these are two extreme examples. So how we can control is while creating any GIS feature, point line or polygon, you can define what can be the maximum vertex density. So if I say that two vertices should be at least 1 meter away, so what will happen is the software will not allow you to create any vertices within 1 meter distance. So maximum density we can decide. Of course, minimum density sometime may be very problematic. So, but if you define such that, what will happen is after a first node is created, when you move front, at least it will move away you from 1 meter or 2 meter based on whatever threshold you have set, and new vertices you can create. So in that way, while tracing feature, you click on one, right? So you click on one, then again, so you can keep digitizing whenever shape is changing. Wherever you want smooth transition, you should make sure that vertices are very nearby. If vertices are near, you will see a smooth curve. If vertices are far away, you will see a sudden jump or what is a step linear function. So I told you that most of the time you will be using manual digitization. The problem with the automated digitization is that you have to put a threshold to determine a line or point feature from the hard copy map. Then it will only work when there are very clean maps are there. So generally hard copy map, it's hard to find a clean map. So there may be some dots and other things can confuse. And still there are a lot of manual editing will be required, or what say, not manual, automated scanner can work, it can identify a linear feature, polygon feature, but lot of editing, post editing might be required. So that's why automated scanning or is generally not preferred. But if you see example here, if a linear feature you have scanned, so though it's a line, it look like it have a width. So that is again to convert a vector, you have to do thinning. So how I can do thinning? I can take a central pixel and ignore earlier pixel, and it become a thin one. Then after thinning, for each center pixel, you convert them into a raster. So now in the raster, the center of each pixel will become a dot, and once these dots are joined, a smooth line is created. So this way you can do the automated digitization. First identify the black color pixels, then you try to convert them into the thinning. After thinning to rasterization, then find out the center of the raster each pixel and calculate a smooth line. And this is again a theoretical example, but if there is a junction, there is a diversion, so again it will become a semi-automatic rather than automatic, where manual intervention is still required. And many times the editing after the automated scanning is more cumbersome than digitizing from the scratch. So if you have a direct vector or raster data, things are very simple. If you have a direct vector data, like a GPS file, which again we say that, and this is sold in a vector digital format. So this GPS file or GPX file can be directly imported into GIS. Suppose you have some ASCII or Excel sheets with you. GIS software allows you to import this field directly. You just need to tell which of the Excel field is X, which of them is Y, and you have to supply what is this projection system, and it will be converted into GIS vector layer. So if you have a geocoded satellite image, then again is a direct raster. That satellite image can be directly inputted into GIS and used. The output of the image classification. Basically, image classification is a process of assigning each pixel to some class. So if image classification already done, that output can be converted to vector automatically based on the classification value. So they can be directly imported into GIS. So in short, I will summarize. What we do in data inputting and editing is we find out what data we want to input into GIS and what are various sources. So if your source is not digital, you need to convert into digital. If a paper-based map is there, you need to scan and convert into image, right? And if it is digital, there is no problem. Directly you can bring. Then again, digital, you have two possibilities. The digital image may be georeferenced, not georeferenced. Like the smartphone images which you take nowadays are digital, but they are not georeferenced. So the coordinate on your image taken from your smartphone may not actually link with any ground coordinate. So in that case, your task is to georeference. In order to georeference any images taken from the aerial aircraft or any place, you need to find out the control points. Control points are those points or those objects which are visible which can be easily identified in image as well as in ground. And for that, you will calculate. And once you know these ground coordinates of the control points, you can get the mathematical relation between the image coordinates and ground coordinates. And that mathematical relation or the equation is applied to entire image to get convert that image into a new coordinate system. And then you start digitizing. Once it's digitizing, then you can do the editing. Right. So that's it from today. I hope you have gained some understanding. And once you do GIS practical, the concept like snapping, vertex density, tolerance level will have a good impact on your digitization accuracy and subsequently the accuracy of